When we create an induced current, it creates an induced EMF, and that is typically opposing any kind of external current, and that's in a motor what we call a back EMF. EMF that's opposing the EMF that's coming from the source. So in our typical motor applications, your hairdryer, your screwdrivers, etc., you attach it to, at least in the United States, a 120 volt external source, and that motor produces what we call a back EMF. So you notice the battery is going the opposite direction. So we have the current coming across here. That coil is made of wire and it has a resistance, although at a small resistance, and that current comes through, and basically this back EMF is what we put into our model to say that the EMF of the induced current is opposing that external current. So when a motor is turned off, there is no back EMF initially, and it takes time basically to build up. So initially the current is very, very large because limited only by the resistance of the coil. So as the coil begins to rotate, the induced back EMF opposes the voltage change. The current in the coil is reduced, and the power requirements for starting the motor and for running it at heavy loads are greater than those for running the motor under average loads. Okay, so now we're going to look at the back EMF for Tim and his trimmer, presumably in the summertime sometime. The pump says the back EMF is 18. The source is 24 volts, and the windings have a total resistance of 8 ohms. So to figure out the current going through this, I want to use a loop rule. So starting at the battery, I have plus 24 volts, then minus the 8 ohms times the current, and then minus the 18 volts is equal to 0. So once I rearrange this, I get 8I is equal to 24 minus 18. So I is equal to 24 minus 18 over 8, and that should give me all of 0.75 amps. So this formula we could also write as delta V over R, just use Ohm's law, and the total delta V is the external minus the back EMF over resistance, and we get the same thing. So now we want to compute the back EMF when there is no spinning, and so the back EMF goes to 0, so 0 EMF here. And we're going to use Ohm's law again, so I is equal to just delta V for the source over the resistance. So that is 24 volts down here, divided by 8 ohms gives me 3.0 amps, which is a considerable amount of current. So since this is a lot of current, this is several times, over 3 times what the operational current should be. So you might start to smell some burning. You'll hear the motor spinning very fast. Not good for the motor. Turn it off.